This is Aerodynamics podcast number 39, and today we're talking about the effects of the blockage ratio on wind tunnel experiments. So the blockage ratio is when you have a wind tunnel, which we use to investigate the flow around objects and look at the drag and lift, etc. The object itself is going to be taking up some of the area of the wind tunnel. And so what this does is if you have a wind tunnel, let's say, which is 1 meter by 1 meter in cross section for the area, that means you have a 1 meter square cross section, and this object, if it has a cross-sectional area of 0.1 meters squared, it means it's taking up 10% of this area. What this means is that there's less area for the oncoming flow to go through. And then that means that in order for it to go through this reduced area, it needs to speed up due to continuity. So continuity, the equation tells us that particularly at low speeds, so with Mach numbers below 0.3, which is the general rule of thumb for when air is not compressible. So below Mach 0.3 particularly, the flow, there's only really one way for flow to go through a smaller area, which is to go faster. So if you have, let's say, 1 cubic meter coming through with an area of 1 meter squared, for it to go through 0.1 meter square, it has to then speed up by a factor of 10. Now, obviously in wind tunnels, the reduction in area is not that great. Like usually it's maybe 5% or 10%. So it's not that dramatic, but it still does have an effect on the speed of the flow going past the object. If the flow is faster, you're going to have a greater Reynolds number, and that has localized effects. And that's what we're talking about today and how to correct for them. And to do that, we're looking at a paper called Blockage Correction and Reynolds Number Dependency of an Alpine Skier, a comparison between two closed-section wind tunnels. It's an open access paper, so you can find it in the link below. And the reason why I chose this paper is because it does a pretty good job of keeping variables constant between two different wind tunnels of significantly different sizes and operations, and it's of an object that is fairly representative of a wide number of applications. So it's an alpine skier, and they test the alpine skier in two different configurations. So one when they're standing up, the other one when the skier is crouched down. So they're different geometries, and that has an effect as well, which we'll find out. So let's get in with the paper. They say that the purpose of the study is to determine what the effects of the blockage are on the results of the wind tunnel. So the effects on the drag and just the flow. And they said that the results indicated that a significant blockage effect, which needs to be corrected for, does occur. And they looked at different blockage ratios, and one's called like an optimized blockage constant. They use something called Maskell's blockage correction method, which we'll get into. And they found that by using that, they can reduce the error between the two wind tunnels from 7.7% to 2.2% on average. So what this means is they put this skier into these two different wind tunnels, and each one was giving a slightly different drag. And by using a correction factor, they were able to get these two values much closer together. And this value was fairly consistent among different velocities and different positions. Now, there are limitations to that, which we'll get into. But let's describe the situation first of all. So they say a substantial component of total braking effect on a skier is caused by aerodynamic drag, particularly in the high-speed disciplines of Super G and downhill, and that's true. So particularly for Super G and downhill, on the straights, a skier's main component of resistive force is going to be drag, and when they're in the air as well, so sometimes they get a little bit airborne. But when they're going around tight corners, then the main resistive force is through the edges on the ski and the snow. But a lot of the time it's the aerodynamic drag. So this is a good application. And then they describe the blockage effect. They say when a bluff body, such as an athlete or mannequin, is placed in the test section, particularly a closed wind tunnel, the airflow is forced through the open space around the body, and it may be accelerated due to continuum mechanics. This is what I was mentioned earlier, where if you have a closed test section, you have a certain amount of area. Once you start taking some of that area up, you have less area for the flow to go through. That means that it has to speed up. And this can affect the drag measurements, but more importantly, it affects the flow physics. And the reason why it affects the flow physics is because we'll get into more later on, but just straight up, if you have a faster or slower flow, that's going to affect the Reynolds number, and the Reynolds number does affect what flow physics you get. I actually did a good podcast on the Reynolds number. It's podcast number 35. So if you want to learn more about that, check that podcast out so you can understand how the Reynolds number does affect flow physics. That was for a high lift wing. That was quite interesting. Moving on with the blockage ratio, they say that the magnitude of the blockage effect depends upon the degree to which the body blocks the wind tunnel test section. So the more it blocks it, the greater this acceleration of the flow occurs. And this is normally quantified as the ratio between the body's projected frontal area and a test section cross-sectional area. And they call it here the blockage ratio, which is a common way of calling it. And this is usually expressed in a percentage. So 5%, 10%, whatever. They go on and they say that there's no precise agreement as to what blockage ratio you will need to start applying corrections to. So they say here, for example, there's some authors who say that 5 to 10% is when you should start doing it. Another author says, or other authors say above 10%, others say above 3%. And in my experience, it's definitely 5% or above. For most applications, once you start getting even past 3%, you do get significant effects on the drag and the flow physics. So if you can, you should always be applying correction factors, because even at 1%, that is an effect. And if you can accurately apply a correction factor, then you should. That doesn't mean that you're going to be getting the right flow physics. It just means that the drag that you're getting is going to be closer to the actual value. So they want to determine here what correction factor they can use and what ratios, blockage ratios, are important, and when do you need to consider in earnest. And they go through this equation called Maskell's equation to estimate the blockage in a closed test section. So in other words, when you have the uncorrected drag, how do you find the corrected drag? And if you're just listening to this, I'll describe the equation. If you're playing along at home with the paper, you can see it right here as well on page 2. And what it is on one side, it has the uncorrected drag divided by the corrected drag, then equals on the other side 1 plus theta, which is the blockage constant, times the uncorrected drag, times the blockage ratio. So everything here is fairly normal. Like you have uncorrected drag, the corrected drag, but then you have the blockage ratio, which is easy to calculate. The only thing that's difficult to calculate is theta, which is the blockage constant. And they say that this is an empirical constant determined by the base pressure coefficient and the aspect ratio of the bluff body. So what this means is you do a bunch of tests, you figure out what a good theta value would be, and then you use that from now on. It's a lot like actually in CFD when they're calculating different values that you should use for K epsilon and K omega equations. If you know about that, that's a good analogy. And they say that based on data from a normal flat plate, theta of 2.8 with an aspect ratio of 3 has been determined. Alternatively, for a bluff body with an infinite aspect ratio, Maskell showed that theta should be 0.96. So there's a massive range, 0.96 to 2.58, and there are other values there as well. And then some other authors looked at the correction factors for circular cylinders in different flow regimes, so laminar, turbulent, and transitional. And they found that none of these correction factors were valid for every flow regime, and that's because the flow physics changes. So I think now is a good time to talk about the benefits and the limitations of the correction factors. So obviously the benefits of the correction factors are that you can then determine what the real, like I say that cautiously, the real drag coefficient is, but the problem with the correction factors is that it's not really actually correcting the flow. The drag and the lift and the moments and whatever you want to measure, they're a product of the flow physics. If you're not getting the same flow physics, then you're not getting the same values in earnest. You might be getting the same overall value, but the way you're getting there is different. And that means your flow physics is different. And the correction factors do not correct for the flow physics. Now, there are other things that you can do, such as streamline corrections and this and that, but they're a whole other topics to discuss. Just blockage ratio alone cannot correct for flow physics, and that will give you different drags. So this is fine from an engineering point of view. From a research point of view, when you want to understand the flow physics, it's not so much the case. So it's a bit touch and go. Moving on with these researchers who investigated these circular cylinders, and they found that no blockage corrections were good for all regimes. They said that they proposed combining two different correction models where Maskell's method with a theta of 0.96 was used for subcritical flows, so Reynolds numbers below 200,000, and then a different formula when the Reynolds numbers were above 200,000. So again, this is showing that when the Reynolds number changes, the flow physics changes, and the method that we're using is going to be different. And the correction factor, again, it's based on flow physics. The drag and lift are just numbers at the end of the day. Then they move on to their methods, and it's really cool because they have two different wind tunnels here, two good wind tunnels that they tested these skiers in. They had one in Norway and then one in Milan. And the one in Norway was a smaller one. The one in Milan was much bigger. It was about 3 times the cross-sectional area, 15 meters squared instead of 5. It could go to much higher speeds, 55 meters per second instead of 25. Now, one thing that we should discuss is the thermal intensity. So the thermal intensity of the wind tunnel in Milan, the bigger one, was 0.1%, which is really good. The one in Norway was 0.24%, which is still really good, but it is different. And I also did another podcast on the effects of thermal intensity on the flow and flow physics. That was podcast number 32. If you want to look at that and learn more about why thermal intensity is so important, check that podcast out. But in a nutshell, thermal intensity does affect the flow, and it does affect what Reynolds number the flow will be turbulent. Now, the good thing with this is for much of this experiment that they did, the flow is already turbulent, so the thermal intensity is not going to make too much of a difference in this particular instance. It may make a little bit in the laminar regions, but overall it's okay to compare these two wind tunnels. If it was like 0.1% and 2%, then that's very different, and that would be very bad. But here it's okay. At least that's in my opinion. If you disagree, feel free to let me know in the comments and why. I'm always interested in learning other things. So moving on, they say the test procedures were identical at both wind tunnels. The measurements were done in steps of 5 meters per second up to 25 meters per second, and in the Norway one, and then up to 35 meters per second in the Milan one. And they tested the skier in 2 different positions. So the first one is in a sort of a standing position and with his arms out, or her arms, I don't know, their arms out, whatever. And so sort of like when you have the stocks at your side sticking out and you're trying to turn a little bit. This is also kind of what it looks like when they go through the air. Then in the second position, there's a tucked position. So the skiers crouch down in a very streamlined position. And this is to get maximum speed on the straights and on fairly shallow turns. Then they measured the frontal area of the skier, so they know what the frontal area is for the drag and their calculations, and also the blockage ratio. And what they found was that the method of the frontal area measurement has several important limitations. So this is quite good. They go through what potential differences there were between the 2 tunnels. And what they said here was when they measured the skier in the 2 different tunnels, first of all, there could be a difference just because the skier took on a slightly different position. So maybe the skier's head was slightly down or slightly misaligned or this and that. That would create an error. Another error is that the angle might be at different positions or different focal lengths. That would also create another error in the image due to distortion of the image that it sees. So these are minor errors that can creep in, and it's good that they're doing such a thorough analysis of their errors, and it's just something to keep in mind. Then they talk about the blockage effect correction. So they're looking into Maskell's method for the blockage correction, and because that's the most widely used. And so they decided to look into using both of the values of theta equals 2.58 and 0.96, as they found with other studies, but also to develop their own and see how these change. And they said that the different thetas, so the correction factors, were evaluated by examining the mean percentage absolute errors between the results from the 2 wind tunnels. So what the differences were between the 2 drags of the different wind tunnels for the different configurations for the different speeds. And now they get into the results. And they say, for comparison between the 2 wind tunnels, the mean percentage absolute error was used. The results for both separate and combined comparisons of the standing and tucked positions for the evaluated blockage constants are presented in Table 2. And in table 2, they have the mean standard error in measurements was 0.5%. And they have different thetas, which were optimized blockage constants for standing, tucked, and both positions combined. So what they say here is, if you have, depending on this skier's position, the theta that you should have is different. And this is a very good result because it agrees with theory, where if you have a different geometry, that's going to have different flow physics, and your theta is not going to be the same. So when they used the pre-found ones of 2.58 and 0.96, yeah, it did bring down the overall error slightly in one case and quite well in the other case. But when they made their own, it brought down the error even more, and it was better. Now that doesn't mean that the flow physics is the same or are the same. It just means that the drags are similar. And then they went and said that the in table 2, the largest differences in the drag coefficient measurements between the two wind tunnels were measured when the blockage corrections were not performed. So that means any blockage correction factor that was applied benefited the results. And overall, by choosing a theta, so the correction factor of 1.21, the resulting error was only 2.2% overall, and that was the best case that they found. And now here they have a really good figure, it's figure 3. And what they have here is they've plotted the uncorrected and corrected drags with a different Reynolds number for the standing and tucked positions. And this is a good figure because it illustrates just how these corrected and uncorrected, or the corrected values can change with increasing Reynolds number. So with their correction factor of 1.21, at higher Reynolds number, the values agreed far better than at lower Reynolds numbers. And that's because at lower Reynolds numbers, the flow physics is almost always in like almost every application really. There might be some minor applications, but generally speaking, at low Reynolds numbers, the flow physics is very sensitive to the Reynolds number. When you get to higher Reynolds numbers, the flow physics becomes more robust, which means that the correction factor will be more robust too. And that's what we find here. At higher Reynolds numbers, the errors are within 1%, but at low Reynolds numbers, they're now 5, 6, 7%. So they're even more. And they say that it is worthwhile to point out that while theta equals 1.21, which worked well in correcting both the standing and tuck positions at high Reynolds number, it did not work well for the tuck position at low Reynolds numbers, as we just mentioned there. While this may not be a problem when studying high-speed sports such as alpine skiing, it does indicate that further investigation of appropriate thetas for low-speed sports is warranted, again, because of the flow physics is different, and it's very sensitive to the velocity. So in conclusion, the aerodynamic drag and frontal area of an alpine skier and any object in general will be subject to a blockage ratio when you put it into a wind tunnel. The greater this blockage ratio is, the more the error in the drag will be and the change in the flow physics. They looked at this alpine skier here, and they found that the best blockage constants for high and low positions were 1.15 and 2.52, and they gave mean absolute errors of 1.5 and 1.8%. But if you want to come up with a general, like a universal correction factor, then a theta of 1.21 gave an error of only 2.2%. So if you want to get very particular about certain geometries, you can make the theta more accurate. If you want to come up with a global value, then you're sort of stuck with a one size fits all approach, which doesn't fit anyone perfectly. But this is what you need to do if you want to correct for your blockage ratios, or get to a bigger wind tunnel if you can afford it. So that's the end of this podcast. Make sure to like, subscribe. Let me know what you think in the comments about these correction factors, if you have any experience with developing them. And check out Aerodynamics, check out the instrumentation we do. We do something called the Atmosphere Hawk. And speaking of correcting your results or your experiments, that also does that in a similar way, in that it measures the temperature, barometric pressure, and humidity of the air that you're experimenting in. And why this is important is because these values affect the density of the air. And if you're not taking account of that, then you're getting that error into your results. So you can't really accurately calculate the velocity of your wind tunnel, because the velocity of wind tunnel is determined by the density of the air. You can't accurately determine what the drag coefficient or the lift coefficient of your object is. And even the flow physics will be different because the Reynolds number is different. And your Reynolds number will also be different when you calculate it. There's a whole bunch of ways that the density does affect your results. So it's good to get that error out of the way. The Atmosphere Hawk does that for you. Check that out in the links in the description. We also do traverses and PIV, which are methodologies, and they can really enhance your research capabilities. If you want to become a better aerodynamicist, so for example, in this podcast and other podcasts, we go through theory and CFD and experimental setups. They all help you become better. Our courses also do that. We focus on CFD. We have ones for CFD, we have ones for experiments, and we have ones for theory. So if you want to get better at any of these, we have beginner, intermediate, advanced, and expert courses. And we also have the conference put on every year. I'm still thinking about the Atmosphere Hawk, but the conference put on every year is called the International Aerodynamics Conference. We put on every year for aerodynamicists to get together and talk about aerodynamics. So if you want to do that, check the link in the description as well. I'll see you in the next podcast. Peace out.